Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic, layout and lambda based designs. In the previous topic, we have discussed the introduction towards stick diagrams. So what are the rules to draw, what is meant by a stick diagram, and rules to draw a stick diagram, and NMOS based stick diagram and its inverter stick diagram we have taken, and CMOS rules to draw a stick diagram, and CMOS inverter stick diagram we have completed. So in the present topic we will discuss what are layout rules and lambda based design rules in VLSI. After completion of this topic, you will be able to illustrate the lambda based NMOS design rules, and you will be able to examine the various contact cuts. Going into the details, so this is how a layout will be represented as. For example, in stick diagram, the P diffusion is represented with the same yellow color but with a line. There is no dimension we have used, with a single line, and N diffusion also with a single line that is in green color, but we have not used any dimension. But here you see exactly in layout what we need to, the extension of stick diagram, the same color code we will be using, but the width of P diffusion to be maintained is 2 lambda. Similarly, width of N diffusion to be maintained is also 2 lambda. And whereas the separation of the distance between two diffusions, whether that is N diffusion or P diffusion, between P diffusion and P diffusion this should be 2 lambda, between N diffusion and N diffusion this is 2 lambda, and whereas here it is wrongly marked. In place of P diffusion, this should be polysilicon, right? Red we use for poly, red color code. So here also polysilicon is again going to have similar width of a diffusion, that is 2 lambda, and separation between polysilicon and polysilicon is 2 lambda. Whereas the separation between a polysilicon and any diffusion, whether P diffusion or N diffusion, is 1 lambda. And whereas coming to the metals, this is metal 1. So few designs may require metal 2 also. Magenta, the color magenta represents metal 2, where blue we will be using for metal 1. So the width of the representation of the layout of metal 1 is 3 lambda, and separation between metal 1 and metal 1 is 3 lambda, and whereas width of metal 2 layout representation is 4 lambda, and whereas metal 2 and metal 2 the distance of separation is 4 lambda. Hope this is understandable. Few more details of layouts. So here what you are seeing, blue color coding represents what? A metal, and black color represents a contact. So how to make a contact with a metal? How to represent a contact in a metal? So fundamental thing is in total what should happen? This metal boundary should be 4 lambda by 4 lambda, in which the metal contact will be a square shape with 2 lambda by 2 lambda side, on each side, and whereas separation of the contact through the edge of the metal layer is 1 lambda. So this is 1 lambda, this is 2 lambda, and this is again 1 lambda. Put together total 4 lambda. So this side also, this is 1 lambda, this is 2 lambda, and this is 1 lambda. Put together this is 4 lambda. So this is how a contact layout should be made in a metal layout. So this is also one more metal with contact. So what should be the distance of, minimum distance of separation between each metal is 2 lambda. And now one more aspect of here. See, whenever from a contact, if you want to make an extension with a diffusion, yellow color is a P diffusion. So P diffusion need to be connected with a contact to a metal. So what is the width? Previously we have discussed of the P diffusion is 2 lambda. And now whereas when you are having extension of the metal from the contact towards any device, see here as we have mentioned, this separation is 1 lambda and this width is 2 lambda, so put together 3 lambda. So you should use a width of 3 lambda in order to extend it into the device. Then coming to the transistor representations, as we have mentioned in our previous topic in stick diagrams, a polysilicon overlapped with a diffusion will represent a transistor. See here, this red color is polysilicon and this green color is N diffusion. Diffusion 2 lambda width, polysilicon 2 lambda width. So this overlaps makes an NMOS enhancement mode transistor. And here what is the rule you need to follow is the extension of this polysilicon from the diffusion is 2 lambda. Extension of this polysilicon from the diffusion is 2 lambda. Similarly, a polysilicon when overlapped with the P diffusion, this yellow is P diffusion, this makes a PMOS enhancement transistor. Here also the similar dimensions we have. Whereas NMOS depletion, we have the same dimension, but one thing to observe is this one. This is called as an implant. The yellow color encapsulation what we are using is the implant. Depletion will contain an implant. So here the rule is, in all sides of the implant, the extension should be, if that is a diffusion, diffusion should extend 2 lambda ahead, 2 lambda ahead, polysilicon 2 lambda ahead, here also 2 lambda ahead. Total depletion, that is implant size, should be 6 lambda by 6 lambda. So this dimension totally is 6 lambda and this dimension from here to here is 6 lambda. Whereas lambda based design rules tabulated here, whichever we have discussed now. For polysilicon, what should be the minimum width and minimum spacing? For N and P diffusions, what should be the minimum width and minimum spacing? For N well, what is the minimum width and minimum spacing? P well, minimum width and minimum spacing 3 lambda by 3 lambda. Metal 1, minimum width and minimum spacing 3 lambda and 3 lambda. MOSFET layout rules, few more. Poly overlap. So minimum extension, as we have seen in our previous slide, minimum extension should be 2 lambda. Whereas poly N diffusion and P diffusion, the minimum spacing should be 1 lambda. This we have seen pictorially. And MOSFET width should be 3 lambda. Whereas N diffusion or P diffusion, if you have a contact, exact size is contact 2 lambda by 2 lambda. And to the space to the edge is 2 lambda. Whereas poly contact, we have exact size again 2 lambda by 2 lambda. And then minimum space to poly edge is 2 lambda. These things pictorially we have seen in our previous slide. Now see a small example to consider all things at one place. See here, this is a polysilicon where 2 is marked means that is 2 lambda. And see inside a polysilicon there is a contact. So this contact width is marked here, that is 2 lambda. So in all the directions that will be 2 lambda. And extension of polysilicon beyond the contact 2 lambda on all the sides. And here this green color is N or P diffusion, you may consider it as, where the width here is 3 lambda. And see here this contact is again 2 lambda by 2 lambda. And extension of the diffusion is 2 lambda on either side. And one more important thing is, see here this separation between the diffusion and poly. How much separation should be there? 1 lambda according to our rule. Hope that is clear. So similarly we have few more rules to be maintained for an N well. If you have an N well, so in fabrication process we have seen what is meant by an N well. So for an N well, what should be the dimension is 10 lambda by 10 lambda, and minimum spacing between two wells is 6 lambda. And whereas between diffusions, the minimum width to be maintained in diffusion is 3 lambda, and separation between the spacing between the diffusions is 3 lambda. So drain to source of N diffusion P diffusion to N well is 5 lambda and 5 lambda. See here, N diffusion, P diffusion. So to N well, this is N well boundary, it is 5 lambda. From P plus to N well boundary, this is 5 lambda. Whereas for contact to N well edge, P plus in the substrate to N well, that is 3 lambda. See here, P plus to the substrate in N well, that is 3 lambda. And N plus in the well to N well. See, N plus in the well to N well, this is again 3 lambda and 3 lambda. And whereas polysilicon, when you are considering minimum width, we have discussed already, that is 2 lambda, and minimum spacing is 2 lambda, and spacing between this one diffusion and polysilicon is 1 lambda, this is there. And see, NMOS drain or source extension is 3 and 3. So extension here is 3 lambda. Whereas N diffusion, P diffusion with well spacing, see either N diffusion or P diffusion in the well, you should maintain 2 lambda separation with the well to the diffusion, and in the next well again that is 2 lambda. So minimum dimensions for N well, 2 lambda is the width, P well also 2 lambda, N well minimum spacing is 2 lambda, P well minimum spacing is 2 lambda. And when we have an overlap with N well, then that is 0 spacing. This poly contact, similarly we have a poly contact, this which we have discussed already. And this contact information is also discussed in the previous pictures, just produced in a different way. And this is metal representation. We have already discussed metal 1 with 3 lambda and 3 lambda, and spacing is 3. And see here overlap of metal 1 with poly, how much overlap is there. So this dimension is 1 lambda, and this dimension is 1 lambda, this is shown here. And whereas via, how to represent a via? Via is represented with a cross mark, right? And dimension is 2 by 2, that is 2 lambda by 2 lambda. And via spacing is 3 lambda. And overlap of the metal with via is 1 lambda. So this one is 1 lambda. Via to poly we have 2 lambda. Via to anything, via to poly or via to N diffusion or P diffusion or N diffusion to P diffusion to poly, that is 2 lambda only. Whereas metal 2, the width is 3 lambda but the spacing is 4 lambda, right? And this is the overlap, what we are using 1 lambda for metal 1 and metal 2. So based on this topic, there are few lecture level questions. Please go through these questions and try to answer them. That's all for this topic. Thank you. Happy learning.